Greetings. To continue the solution of our problem, now we are in a good position to know what the properties of our points are. As far as point 1 is concerned, this is point 1, and what we do is to use these values to find the properties at point 1. What we know about point 1 is that P equals 100 kilopascals and X equals 1%. And therefore, we calculate its properties like V1. I would go with this one in detail, and then the rest I will leave it for you. V1 would be Vf, which is 0.001043 plus 0.01, which is the quality, times Vg minus Vf, which is 1.6941 minus 0.00104. And V1 would be 0.01798 cubic meters per kilograms. With a very, very similar practice, with a very, very similar equation, we may also calculate U1 to be 438.282 cubic meters, kilojoules per kilogram, and H1 to be 440.085 kilojoules per kilogram. And therefore, we have all properties of point 1. What happens at point 2? At point 2, we know that the pressure P is 2000 kilopascals. Also, we know that V is the same as above because neither volume nor mass has changed. I would have a comment on this later on when we write down the mass conservation equation for process 1, 2. But for the time being, let's accept that specific volume would remain constant between 1 and 2 because mass and volume both remain constant. So V2 is 0.01798 cubic meters per kilograms, and therefore now we are in a position, since we know Vf and Vg, we are in a position to calculate X, and X would be 0.01798 minus Vf, which is 0.001177, and divided by Vg minus Vf, which is 0.099587 minus 0.001177. And the outcome is 0.17, which still tells us that the quality at point 2 is 17%. What has happened? You see, the point 1 and point 2 are very close to saturated liquid. But, you see, point 3, as compared to this point, has moved farther to the left. It's much closer to the saturated liquid point. And therefore, the same, almost, the same specific volume would have a much higher quality for this line than for this line, because Vg here is farther away to the right. So once we have x, just similar to this part, we could calculate U2, which is 1193.93 kilojoules per kilograms, and H2, which is 1229.7 kilojoules per kilogram. So now we are quite clear about point 2. We could move to point 3, which point 3 is just saturated vapor, because the problem tells us that the process continues until point until the point that all liquid in the tank is gone and there is only saturated vapor left in it. So, for point 3, what we do? We have everything. P3 equals 2000 kilopascals. T3 equals what? T3 is saturation temperature, 212.38 degrees centigrade. And now, since it is saturated vapor, V3 would be 0.099587 cubic meters per kilograms, and U3 is 2599.1 kilojoules per kilogram, and H3 is 2798.3 kilojoules per kilograms. So we now have all properties for all 3 points, except one property which we haven't yet dealt with, and that is mass. We can also calculate mass for all these 3 points. Let's do it here. M1 equals V1 over V1. And if we put numbers to it, it is 1 to 0.01798, and therefore M1 would be 55.62 kilograms. M2 is also the same. M2 is also the same, 55.62 kilograms. But as far as point 3 is concerned, because some vapor, some steam is let out, then M3 would be 1 over 0.099587, and that would be 10.041 kilograms. Okay, so once now we have all properties at points 1, 2, and 3, please note that these properties are steam properties. It have nothing to do with our problem. We have just read them from the table, and they are true for steam and for every process that happens to steam. These properties are our problems. In fact, our problem happens on these points. A second note which you have to take care of, and it's very important, is that, look, when we say the quality is 1%, it doesn't mean that we have a mixture of vapor and liquid. No, it's not the case. You see, we have some liquid here and some vapor here. Quality just gives the ratio between what is happening here and the total mass inside this tank. So when you have quality of 50%, it means that there is some liquid, some vapor. There's no mixture. There is no mixture. And therefore, when, look at this, you have vapor standing here up and liquid down. And therefore, when the valve opens, only vapor goes out. There's no liquid going out unless there's a valve underneath. If there's a valve at the top, only vapor goes out. Okay, so we have to be careful that the values here for Vg, Va, and the values here just mean the ratio between the mass inside, the mass of vapor inside the tank, and the mass of liquid inside the tank. Somehow, of course, quality means the mass of vapor to the total mass, but it indicates how much vapor we have, how much liquid we have on the mass terms. Okay, so a quality of 100% means we have all liquid, all vapor, and no liquid, and the quality of 0% means that we have all liquid and no vapor. And these are our conditions. Now that we know the properties of all 3 points we are concerned with, the next step is to see how these points relate. Generally, there are 2 ways to relate different points of different processes. The first and very simple one is to tell us that some property remains constant between 2 processes. For example, look at this between processes 2 and 3 in this figure. Between processes 2 and 3 in this figure, we are told that the pressure remains constant. So when in fact we are given one property of point 3. We also are given that point 3, all liquid is gone and there is only the saturated vapor in the tank. So we know that point 3 is saturated vapor. So one way of defining the process is telling us what remains, what property remains constant in that process. In process 1, 2, specific volume remained constant, and that was the interpretation we made from what the problem was saying. Look, it's a very important point in problem solving to interpret what you read in the problem definition to the solution method. I mean, you have a problem and it tells you a few things. It has a language of it. For example, it says that we have a tank. It's a closed tank and we just heat it. What does it mean to have a closed tank that we just heat it? It means that during this process, neither the volume changes nor the mass changes, and therefore specific volume remains constant. That is a property that we are looking in the process, and that's what happened in process 1, 2. The second point is they tell us that there is a volume and there is a valve, and that lets the steam go out at constant pressure. Of course, when steam goes out at constant pressure, pressure remains constant. But there's another value to this statement. And another reduction from this statement is that properties at point 3, that means the exit properties, are all saturated vapor. So we can make 2 conclusions from just this statement in the problem. And that is one thing that we have to try to learn, that whatever says in the problem, we have to interpret it to the language of thermodynamics and to the equations, and that is what we shall practice. So, uh, what we do now is try to simplify the governing equations. The governing equations that we have are these equations. And these equations, the first two are those that we are concerned for the time being. The first one tells us the change of mass within the control volume is a function of the inlet mass and the exit mass, and nothing else. That's very important. The white to the right is very important. It means that there is nothing else that can affect mass. Mass only changes with mass. In the present problem, we have no inlet mass, no exit mass. So the mass in the control volume remains the same. And we have to write it just like this. Look, we have to write for process 1, 2. Process 1, 2. And the mass conservation law simplifies to M2 minus M1 equals 0. In fact, the change of mass between points 1 and 2 is only a function of inlet mass and outlet mass. And since there's nothing in or out, then therefore, from the mass conservation law, we conclude that mass remains the same. We may also write this equation in a different way. It says we could write it V2 over V2 minus V1 over V1 equals 0. And since V1 equals V2, that means V2 equals V1. That's the conclusion I made here. And I said just because the volume doesn't change, mass doesn't change, therefore specific volume doesn't change, which is of course correct. But the important thing is that we could also conclude this from the mass conservation law, and that is the language of thermodynamics. That is the language of thermodynamics. To write the mass conservation law for process 1, 2, write it like this. And since V1 and V2 are equal, then mathematically we conclude that V2 equals V1, and that is the correct way of doing things. You see, mass conservation, there are two methods for simplifying mass conservation law or any law, any of the other laws. And I wish to discuss it just briefly before I move forward. You see, mass conservation law tells us that dmCv by dt equals m dot I minus m dot E. And there are two types of processes which we usually study in thermodynamics, two basic types of processes. And the first process is the process where there are no inlet or outlet mass. We call it a system where there is no inlet or there is no outlet. And therefore, there should be, for the process, an initial and final point. So we say M2 minus M1 equals 0. So this is a process between a defined initial point and a defined final point pass. So we say defined initial and final points. Okay. Now, sometimes nothing happens inside the control volume. There is only mass coming in and mass going out. So what happens is that there's no change in time with what happens in the control volume. So this is zero. There is no change in time. There's no initial or final state. And therefore, we could conclude that zero equals m dot I minus m dot E. And therefore, m dot I equals m dot E. That means whatever enters the control volume goes out, and that could go indefinitely. There is no initial or final points. Of course, there are some problems which combine these two. There's both mass coming in and going out, and um, there are changes control uh, within the control volume. But if we learn these two basic cases and we understand these two basic cases, then you could combine them to learn from other different cases as well. The other general case could be very easy if we learn these two. And the important point is that we would do the same process, the same type of thought for all other equations and other laws. I mean, it means that will have a similar definition, a similar division for the first law of thermodynamics and a similar division for the second law of thermodynamics. So we have to take a note of this one. Now, let's return to our problem. And for process 1, 2, we see what mass conservation law tells us. And therefore, we can conclude that M2 equals M1, and we have a value for M1, which is 55.62, 5.62 kilograms. In fact, what we have calculated here from our general knowledge, now we can calculate it from a thermodynamic point of view, and with the instrument thermodynamics gives us for such calculations. Okay, now let's write the first law of thermodynamics for a system for the same process 1, 2, where there is no mass in or out. So we have M2U2 minus M1U1, which is the final energy of you remember what the energy was? The energy E was M times E, and this was M times U plus V squared over 2 plus GZ. And for the present problem, we ignore these two terms, and so E is mu, and so the left-hand side of the second equation, just underneath my picture, would turn to M2U2 minus M1U1, and that equals Q12. There is no mass in or out for the first and second terms on the right, and heat transfer is here. There is heat transfer, and so there is no moving boundary. There is no work, and this is our equation. Putting numbers to this equation, it would give us 55.62 times 1193.93 minus 55 0.68, mass doesn't change, times 438.282 equals Q12. And after calculation, it gives us Q1 as 42,029 kilojoules. Of course, 0.4, there's a 0.14 to it as well, which would equal 42,029 megajoules. And that is the heat transfer required to just increase the pressure from 100 kilopascals to 2000 kilopascals. So we have the heat transfer. Of course, heat transfer only finds meaning in the process. And for the points, we have only properties. Remember, look at the equations, the second and third equations in the picture just underneath. And what you see here is that these are the change of mass. Here you have change of mass, which is a function of inlet mass and outlet mass. Okay, these are all functions of mass, but these three terms, heat transfer, work, and entropy generation, which we shall take care of later on, are functions of process. They're not properties, they are functions of process. And therefore, when we write equations, first law for the process, we could calculate Q, which is the heat transfer. In thermodynamics, we teach you no way to calculate heat transfer. Heat transfer is calculated just from this equation or from this equation, from any of these two equations. In another subject, which is called heat transfer, all they are concerned with is to calculate heat transfer with the knowledge of temperatures, velocities, and other properties. So we have now simplified this equation. There is no work, there is no inlet mass, there is no exit mass, and therefore the change of energy between cases 1 and 2 would be a function of heat transfer and work. The work is not there, so it's only heat transfer. You see here again, just like what we did with the mass conservation law, we could do it here as well with the first law of thermodynamics. I mean, here we changed dmcv by dt for between stations 1 and 2, and now for decv by dt, we have turned it from between points 1 and 2, between conditions 1 and 2, as m2 q2 minus m1 u1. So this is a practice between two stations when we know some initial point and some final point. So we have here all calculations for process 1, 2. We shall continue the rest of the solution in our next video. Cheers.